Hello, data experts. Are you able to hear me? Okay, happy to be here speaking to you about what we are solving at Wayfair India TDC. Um, what we'll be doing is we'll start with a brief introduction about what Wayfair is, about myself, and then we'll jump into the problem that we are solving. Anyone here has heard about Wayfair? Okay, it's not a surprise that not many of you have not heard about Wayfair because Wayfair as a company is not operating in India. We are predominantly based out of US, Canada, and Europe. But 2 years back, Wayfair set up a TDC in India to fast track the development of the technology. And now we have 600 plus engineers working out of India, contributing to the global Wayfair. What Wayfair is. So Wayfair was started as a single product company in 2002 by two young engineers, Steve Conine and Neeraj Shah. Neeraj Shah is an Indian founder. They started with one product, one website, and given the success of it, they kept on adding new websites for each product, and after a period of time, they had 100 websites, one for each product. And then in 2011, they consolidated all of these to Wayfair umbrella as one, all things home. You can consider it as a IKEA, but predominantly online. We do have offline experience stores, a couple of them, and then looking at setting up few more. So what makes Wayfair stand apart? It's the unparalleled list of SKUs and products that we make it available to our customers, seamless experience across online and offline, and value for money. We are also expertise in moving large items across the globe. As we are home, related to home, we sell large items like cots and sofas and couches and dining tables and whatnot. So we have proprietary delivery network which can seamlessly move items from one part of the world to the other. About myself, I have been associated with Wayfair for about 2 years now. I lead the marketing engineering team here, which also includes the data engineering team. Prior to joining Wayfair, I have been in the IT industry for 20 plus years across marketing and telco industries. So why UDP? 1 year back, about a year back, we ran a survey with our machine learning scientists to understand what are the problems they are facing, what would make them more efficient. So one of the feedback, they had a bunch of feedbacks, but one of the feedback that was relevant to data engineering was the time that they are spending on feature engineering. So before I dwell into the problem, I would like to talk about what is a machine learning life cycle. Paris talked about the different stages of data transformation. He did mention that at one point of time, it's also made available to analytics engineers and data scientists. Here we are. So most of the data platforms are focused on making the data available for analytics, business intelligence, dashboarding, etc. Right? Not many are catering this data to ML scientists. So every ML scientist have to, whatever data they need, they have to independently create pipelines to make their features. Going back to the ML lifecycle, ML lifecycle typically involves 4 stages. What we call it as a model engineering, model training, model deployment, and model monitoring. And if you think data scientists, they spend most of their time in writing models, that's not true. They actually spend a lot of time in analyzing, cleaning, transforming the data. So they want to make sure the data that goes into the model is perfect. So you would have heard about this in the data world. Garbage in is garbage out, right? So they spend a lot of time in making sure the data that goes into the model is perfect. So what they do is every time they have to come up with a new model, they come to the data engineering team and get a new pipeline created. And this takes about 4 to 6 weeks. And then when they have to create features on top of the pipeline, that takes n number of weeks, right? So we wanted to reduce this. We wanted to reduce the time taken for the MLS to identify their feature set and to make it easier for them to believe that the data that they are using is curated, good quality, has been cleansed, etc., right? So here we are talking about two types of data. We talk about a seed data and we talk about a feature data. Consider seed data as a primary key of a table, right? It's like in our e-commerce paradigm, what the user is. How are we identifying the user? Customer ID, device ID, etc., right? What the user is. What did they see? Did they see a product? Did they see a banner? Or did they see an ad on our system? What did they do with it? Did they just see the product? Did they add them to a cart? Did they purchase it? Or did they, let's say, return it? Where did they see it, right? Did they see it on our first page? Did they see it on an external ad? So these are primary data that is called the seed data about a user. The seed data is used to create features. What are features? Features are something like, what did the customer browse for the last 7 days, or 30 days, or 90 days, or 365 days? What did the customer purchase? Where did they purchase from? These are derived from the seed data. These are transformation, aggregations, and all done from the seed data. So from a seed data, hundreds of features can be created because you have a n cross n cross n matrix, right? Like on the 4 parameters, you could create an n cross n matrix. So the feature store is that. And then the model training, there are different kind of models. You would have known about it, supervised, unsupervised, etc. Here we are talking about supervised model, where the data, input data and the output data is labeled. Within supervised, we have classification, we have regression, vector models, and even neural networks, right? There could be different type of models. The ML scientist is going to select the right model for solving the business problem that he wants to solve for. And then he has the data now, he has the model, so he's going to iterate the model with the data and look at the output. Is it performing, not performing, and then tweak the features, add features, delete features, and look at the features and deploy and continue to monitor whether the model is continuing to performing as per the expectation, or is it drifting, and make changes to it. So this is the MLS lifecycle model. So what we noticed is each MLS scientist is going through this independently. There is no centralized feature store, there is no centralized seed store, and it takes up a lot of time. So what is the proposed state? So we wanted to create a centralized store for keeping all the seed data. So as I mentioned before, seed data is nothing but placements, customers, products, and actions, and then create features from it, create training data from there, and then all the MLS scientists can access this for their model instead of they creating it one by one for themselves. So how did we achieve this is something I'll be going deeper in the further slides. So before I go into the architecture, I wanted to quickly talk about Lakehouse architecture. Given that we have all data experts here, I'm sure you would have already heard about Lakehouse architecture, but wanted to quickly touch upon what is Lakehouse architecture. So long back, when the data evaluation started, we had data warehouses. Some of the famous ones are Vertex, Snowflake, sorry, not Vertex, Snowflake, Databricks, etc. So they have tightly coupled memory or storage, and compute. So the data is stored in proprietary format, making it easy for analytics to query the data, visualize the data, and then represent the data. And then we also had data lakes that were there for querying unstructured data, the data that is not structured. So companies came together to make an open source architecture which is called data lakes. This is from Databricks, but data lakehouse is an open source architecture that can be implemented by anyone. Here, it basically makes it easy for both the structured data and the unstructured data to be queried. It separates out the storage layer and the compute layer. So the storage, so that you are not tied up to any particular company. It's not a very proprietary format. So you could use a Delta format, or you could use any format for your storing the data, and you could use any compute to querying the data. And it takes the data into 3 stages. The first stage is where the data lands. So what we call it as a staging stage or a bronze stage, right? Here the data lands as it is. It is basically collected from multiple sources. It could be your in-house sources, or it could be even third-party external sources. Every data is collected and stored as it is without much modification. Here the whole idea is store the data as it is, so that if you want to go back, look at lineage, or if you want to go back and audit the data, and even sometimes rerunning the data if some of the downstream processing has failed, right? So you have the data in place. And then this data is then curated, cleansed, and like for example, there is a test data that we want to remove it, and we want to augment the data. There is a metadata available, and we want to join them, we want to filter it. And that is what is done at the silver layer. Here the data is usually in a third normal form. So this layer is also sometimes used by the analytics for ad hoc analysis. Even the data scientists may look at this layer. After this, the data is aggregated, the business logic is applied on top of the data, and then made available for presentation in aggregated format. This is usually the gold layer, right? And also the silver data can also go into a feature store. Now, what is missing in this whole architecture is this largely built for data analyst and not for ML scientist, right? So we don't see how I can generate features from here. We can put data into a feature store, but we rely on the feature store to do more feature generation. So we wanted to use this framework and build on top of it. So we came up with something called Wayfair Unified Data Platform, which basically takes the data lakehouse architecture, extends it to add further processing and platforms to generate the seed data and the feature set that I was talking about before. So let me talk about the details of these and what are the components that are basically available here. We logically separated it out into 2 modules. These are internal code names. We call the first one as Atlas, the second one as Horizon. In the first one, we have the first component is called fact gen, right? This generates the fact data. This is similar to what a data lakehouse output for a gold, at the gold layer, right? This actually reads from various sources, transforms, cleanses, normalizes the data, converts them to a star schema model where you have the facts and the dimensions, and that's made available in a store. We are a Google cloud shop, so some of these technologies that we use are from Google Cloud, but this is just a data warehouse. GBQ is Google BigQuery is what we use. Equivalent on any cloud is something that we can replace it here. And what we have connecting layer is all DAGs that are orchestrating reading the data, transforming the data, aggregating the data using Spark engines, and then putting them into a fact table. This is largely static tables. There's nothing dynamic about them because we want to make sure that this is valid data that the data scientists can rely on. We are also, on the horizontal layer, we are also applying data quality checks to it. So many times we have seen upstreams misbehave, right? And that causes issues in the downstream. And many times we don't detect there was a problem in upstream, right? There is anomaly in the data. The field shouldn't have been having this value, but we got into a system. So Google has a product called Dataplex. We extended it basically to enable data quality checks. So you can add null checks. You can say this particular data type should be there. All of those checks are done at this layer. So it's actually done in each of the layer, but this is a layer. So that's a fact gen, right? So you have the fact data now. Now, based on this fact data, we generate the seed data and the feature data. So these two are dynamic because we want to make sure we are giving the flexibility to the ML scientist to generate whatever seed data they want, whatever feature data they want, and with a very less friction with the data engineer. So they don't have to come to the data engineer each and every time they want to create a feature. So the second and third boxes are more dynamic, and they are built in a way that they can be either scheduled to generate things on a weekly basis, or by a config can be manually triggered by a ML scientist. So I'll go into the details of how we did it dynamic. And just to complete the flow here, after the feature is generated, we load the feature into a feature store. In this case, we are talking about Vertex AI, which is a feature store provided by GCP. It could be any low latency key value pair store. It could be Redis, it could be Aerospike. But Vertex AI provides certain other functionalities such as governance, RBAC. You could be letting only few data scientists, ML scientists access some of the data, not all the data. And then you have the ML scientist notebook that is accessing the feature store and then using that for training the model. So I'll be talking about how did we make the seed gen and the feature gen dynamic. So here what we are doing is we are generating dynamic tables. These tables have to be generated dynamically, and these pipelines have to be triggered dynamically. So these are not static tables and pipelines. So we have come up with something called a dynamic SQL generator and a schema validator. So we want to make sure the SQL is generated dynamically. There is a template which is parameterized, and then there is a set of configs that has the different actions that can be taken, like join, etc. And once the config is applied on the template, the SQL generator generates the SQL, and then it's validated to make sure the SQL is having the right schema. Once this is done, it's picked up by the DAG. It could be Airflow DAG or any other DAG. In our case, we are using Composer from GCP. But before that, we want to make sure the schema of these SQL tables hasn't changed a lot, right? The schemas have to be well within the schema definition. It cannot, there are certain rules for a schema. You can add a column, but you can't drop a column or rename a column because there could be some other MLS scientist using those columns for their models. So there is a schema definition, there is a schema management engine, and then there is a schema validation. These two are applied, and DAG runs on them and creates the seed table on GBQ. So this is how we are making the data dynamic, and making it self-serve. So if a MLS wants a new seed data, they could come and change the config. They can pick up the input data. They can pick up the output data format they need, put it in this config, and trigger a DAG, and this will be automatically uploaded to the GBQ table. So we spoke about FactGen, which creates the fact tables, SeedGen that creates the seed tables. Then we have a module called FutureGen. So we have a module called FutureGen. FutureGen reuses the dynamic SQL generator and the schema validator. It's just that FutureGen uses seed data to create features. And this could be, as I mentioned before, this could be a lot of combinations of seed data. Many times the scientist needs hundreds of features. They want to evaluate all of them. So a combination of a user versus a product versus an action versus the page in which they took the action, as I mentioned before. FutureGen, it's just that instead of generating the seed data, it generates the feature data. We'll talk about what is the feature generation flow, right? So it starts with triggering the pipeline. The pipeline gets triggered either periodically because the feature has to be refreshed on a periodic basis, or manually by ML scientists coming and changing the config. So then it loads the config, checks whether this config has schema changes or not. If it has schema changes, then it has to go through the schema definition and schema validator to check that if this schema change can be allowed. If it can be allowed, then it goes through the generating the SQL queries. And SQL queries are generated from a template and the config, as I mentioned before. These SQL queries are validated. If there are issues, then they go through an error. The queries are executed. And after execution, the features are validated again. We want to make sure the features are good enough. Again, they go through data quality checks to make sure the features are good enough for the MLS to use. It is prepared to uploading into a feature store, and they get uploaded to a feature store. Could be Vertex AI. What are some of the benefits of putting this data into a feature store? So we could make it available in GBQ or a data warehouse as it is. Feature store provides certain benefits, right? Basically, it can provide auditability. Let's say a feature has changed and we want to see what changed in the feature. We can go back and check. There's audit, time-based audit, or a config change-based audit. It can give us different versions of the same feature. So the MLS can create different versions, test different features, and then use them as needed. It can support governance, as I mentioned before. We want to apply RBAC and say that this set of MLS needs only this data. Let me give access only to this data, right? And it could also support online and offline data. In case of the others, it could be only batch processing. We can't do online. So it's usually a low latency serving system. So it can be used for both online and offline models. This is the system has been is almost ready now. So we are doing a demo with our ML scientists next week, and we are looking at taking it for adoption. So we are hoping that this is going to solve their problem and increase the velocity. Wayfair is like a 14 to $15 billion revenue company, and we spend upwards of $1 billion on marketing per year, and we want to make sure our marketing spends are as efficient as they can be. So we create a lot of models. We run a lot of experiments. What is the right image to be shown to the user? We have seen that just showing a different image from the catalog to a user in the ads have shown improved performance. Changing the color of ads, overlaying ads with certain text showing that this is a Wayfair verified product, there is a sale running on it, and all such things have helped. So these are experiments we run continuously. To run these experiments, we need the models. For the models to work fine, we need the good data. And For the models to be iterated very quickly, we want to increase the velocity of the ML scientist. And that is what, as a data engineering team, we are trying to help. Many times, the data engineering team end up serving the analyst or a looker dashboard or a UI. I invite the data engineers here to start thinking about how they can contribute more, how they can contribute to the data scientist or the MLS. Like, these two terms are used interdependently in your organization, and increase the value of what you can give to your organization. So that's about my presentation. I think